That
Hopefully that
is kind of
works.
one of the go-to like architecture if you want to just like get up and running with any type of like image recognition type stuff. Like last workshop we did transfer learning and we used ResNet as the architecture. So it's very much a go-to and something that you should have in like your arsenal of ML tools. Um, so who here like looked at the paper beforehand? Anyone? Okay. No problem. So I went through and I highlighted the first part before we get into experiments. The experiments is just kind of comparing to how other architectures did. But I really want to talk about how how you should like approach a paper, break it down, and find like the actual important like sentences in here that's going to really like explain why ResNet does as well as it does. Um, and so the first place you should start off with is really just so let's say you're like scrolling through archive, which is this thing right here. Or a nicer interface, this loads, which is, we go down here to statistics, we have machine learning category. And so all these papers were from like right here to the top, were just published today, like just thrown on here. And anyone can like submit to this preprint server is what it's called. So it's just what people put on to say, okay, I had this idea at this time. So it's kind of like indexing that you came up with this at this time. Um, so here there's just like so many different things. How do you like break it down? How do you think it's like a good paper to read? The main thing to use, let's say, okay, what the hell is inferring dynamical systems with long-range dependency through line attractor regularization? What the fuck does that mean? So the main thing people do is just read the abstract. Like you'll have people just go through like 20 different papers, only read the abstract, um, and then if the abstract and the title like kind of get your interest, then you can go check it out, and then people just go through, look at the graphs, see if things are making sense. You might see something where it's just hella math happening, so it's like I don't have time for this, skip it. Um, so the very first thing you should probably do is just scan the entire paper. Does anything jump out? Are the figures good? Is there some really convoluted math happening that probably won't like tell you much about some ideas? Just like an author trying to be fancy here. Um, so if everything like comes through like something that you want to do, then I always like to just go through and read the introduction, and then try to find where the model is actually described, and then the conclusion. So in this case, I would go through, read the introduction, okay, what's happening in this paper. I wouldn't look at related work because that's really only going to be useful until you're trying to like, okay, is there any better methods here? What have other people tried? Um, and then I would look for like what's happening, where's the model? And that would be this section, deep residual learning. This is like the pure meat of the paper. This is ideas. This is them saying why they're doing what they're doing. And then there's always going to be a section on experiments. You're always going to end up with a graph that says our graph does better than their graph. So that's kind of just if you find a paper where it's not doing better, or you can see some results where it's like only do better in certain cases, that's probably not going to really reveal itself until you start digging into these experiments. If it's very apparent on the graphs, then I don't know what the hell the author was doing. And then I always like to read the conclusion. Sometimes the conclusion is really just a rehash of what's happening in the introduction. But sometimes it really talks about, okay, implications, future work, things that they haven't really solved. So if you're looking for new research ideas, looking at people's conclusions, you're able to see, okay, what are things that left for future work? What are things that didn't work quite well for them? But for today, when we go into this, let's read the abstract, go into the introduction, and then the meat of the paper, go through these equations, kind of what do they mean, and why do they make us do better on ImageNet. So the abstract here, let's just read through this. Deeper neural networks are more difficult to train. We present a residual learning framework to ease the training of networks that are substantially deeper than those used previously. We explicitly reformulate the layers as learning residual functions with reference to the layer inputs, instead of learning unreferenced functions. We provide comprehensive empirical evidence showing that these residual networks are easier to optimize and can gain accuracy from considerably increased depth. On the ImageNet dataset, we evaluate residual nets with a depth of up to 152 layers, 8 times deeper than VGG nets, but still having lower complexity. An ensemble of these residual nets achieved 3.57 error on the ImageNet test set. This result won the first place at this conference classification test. We also present analysis on CIFAR 10 with 100 and 1,000 layers. The depth of representations is of central importance for many visual recognition tasks solely due to our extremely deep representations. We obtain a 28% relative improvement on the COCO object detection dataset. Deep residual nets are foundations of our submissions to this conference competitions, where we also won the first place on the test. So the main part of this abstract is really that first half. The last half is them saying, okay, we did better at this, we won these competitions. It's like, cool, good for you. So finding the meat of this, we see that there's this first sentence: we explicitly reformulate the layers as learning residual functions with reference to layer inputs instead of learning unreferenced functions. So the question out of this comes from, what are these residual functions and what are these unreferenced functions? If you read machine learning papers, no one really talks about neural networks that way. So why is it being used in this language in this paper? Then another important thing that I didn't highlight here is this word solely. So they're making the claim here in this abstract that solely due to their extremely deep representations, we obtain a 28% relative improvement. So they're saying why this network does so much better on all these different data sets, on all these different tasks, is solely because of their deep representations. They just have really deep neural networks now, and that's why it's going to do really well. So they're making that claim. Now, that's like intriguing if you're just reading through here, like, oh, okay, so they like found a way to make really deep neural networks. They did all really good on all these different tasks. They seem to have like some idea of why it's happening with this sentence here. So then that's probably something that's going to catch your eye and be like, okay, let's dig into this. Let's read some more. So going into the introduction, they just talk about, okay, deep convolutional networks. It's good for image classification. End to end, we don't have to do any like hand-done like feature extraction. We have levels of features. Those are those convolutional filters, building that hierarchy of different like shapes or patterns within the data. And so we have this line here: recent evidence reveals that network depth is of crucial importance, and the leading results on the challenge ImageNet dataset all exploit very deep models with a depth of 16 to 30. So this being into the introduction right here is taking the point that, okay, all these past ImageNet models have been really deep. So network depth is probably a pretty crucial part of doing well on this ImageNet challenge. And they also state, okay, it does better on other tests too. So it brings up this question right here, and they explicitly lay out this question. Is learning better networks as easy as stacking more layers on top of each other? So people have been doing well with depth. Can we just stack like a shit ton of layers on top of each other, and is that just going to do that much better? And there was a problem with this beforehand. So you used to have vanishing exploding gradients when you had all those layers stacked on top of each other. If you're going back propagating through those, if those were really small, it's just going to keep getting smaller and smaller and smaller, eventually until they vanish. Or if they're really big, they're just going to keep getting bigger and bigger and bigger until they're just massive, and then it's just falling apart. And so then they go and say, okay, we had this problem in the past, but someone already addressed this problem through normalization. So we should go into this at a certain point, but at this point I'm just going to say it allows you to get past that problem. That's what the authors are saying, so we'll take their word for it right now. So going into deeper networks, so we're saying, okay, we have these problems past Let's just focus on making our networks deeper. But they find another problem. When deeper networks are able to start converging, a degradation problem has been exposed. With the network depth increasing, accuracy gets saturated and then degrades rapidly. So you see here, this is what this chart is showing. So if you had a 20-layer network, it's able to train down and then do better than 56-layer network. And that might make sense because we're just stacking parameters on top of parameters. It might take more time for those parameters to get updated such that it's going to be able to perform well on this task. But going farther, there exists a solution by construction to the deeper model. The added layers are identity mapping, and the other layers are copied from the learned shallower model. So if we have one neural network right here, let's just have this be this, and if it performs on some data set, and it gets like 90% accuracy on this data set. This is just some neural network here. You could, in theory, construct another neural network by just adding identity functions on top of here. And identity functions just mean that what's inputted is going to get outputted. So it's just saying, okay, we're going to pass it through something else. And in theory, it will never drop that 90% because it's going to be the same thing coming out of here as coming out of here, because these are identity functions. And this is by construction. So this is like a thought experiment that the authors are proposing here. They're saying, okay, you could just stack identity functions on top of each other, and then you would never do worse because it's just outputting literally the same thing. So what they say here in blue is this existence of this constructed solution indicates that a deeper model should produce no higher training error than its shallower counterpart. That's what I'm saying here. This deeper model here with these identity functions should not produce any higher error. It should do just as well on some data set as its shallower component being this part. And so they're saying what's formally we do not. So now they're saying this is the problem. We should be able to wait. Instead of hoping each few layers. So the key idea is that any neural network that you append on top of here, more parameters, they should be able to learn these identity functions, right? Like over time, it should be able to know, okay, just adding more parameters is going to make it useful. So it should just revert to these identities, and then it would still be able to do just as well. So we shouldn't do worse than that. And neural networks are like universal function approximators. So in theory, they should be able to just find these identity functions, and just stacking more weights shouldn't cause this degradation problem. But the thing is, they observe these degradation problems. So can you exploit this idea of having these identity functions, knowing that if you just had the same output here and literally don't do anything to it deeper down, it would still do just as well? Can we exploit that such that we can have just indefinitely deep neural networks? So this is where they get to the idea of a residual. So now some math comes in. Note, just like if you're reading a paper first time through and you just see a lot of math, it's oftentimes, and I recommend it, to just skip the math, like come back to it later after you get like the general high level idea of what's actually happening. Because you can go here, okay, they're introducing the idea of these shortcut connections without looking at the math at all, because they say here, shortcut connections are those skipping one or more layers. In our case, the shortcut connections simply perform identity mapping, and their outputs are added to the outputs of the stacked layers. So we just stacked some layers here. What if we just took the output here and then appended it there? And now we have that output here, and they're saying, okay, it would be to the extreme if an identity mapping were optimal. It would be easier to push the residual to 0 than to find identity mapping by a stack of nonlinear layers. So it would be easier to just push all these weights to 0, and then when you add this output here, just 0 plus this, you end up with that, and then you do that. So it would be easier to just say, okay, make these all 0, and then just keep what was happening there. So you're learning the difference between adding this and what's coming out of here, and that's this idea of this residual. Does that make sense? We'll do like the little equations in a second. So then moving on, okay, we have this idea of how you can have just add the output here and then just hope that those would just go to 0 instead, and that should do just as well and not have this degradation problem anymore. So then they just go on to say, okay, again, this is introduction paper, so it's kind of like a summary. They say, okay, we present comprehensive experiments. They show 2 points, and those are extremely deep residual networks, are easy to optimize, but the counterpart plane nets that are simply stacked exhibit higher training error. Our deep residual nets can easily enjoy accuracy gains from greatly increased depth. So they do better than their plane counterparts, and they're easier to train. Then you have this related work section here, but we're going to kind of skip that. And then right here is where we have the actual like meat of the problem. So if we say here, if one hypothesizes that multiple nonlinear layers can asymptotically approximate complicated functions, then it is equivalent to hypothesize that they asymptotically can approximate the residual functions. So let's talk about this idea of a residual function. So these are our 2 layers in some neural network, and we have this input x coming into here. And so we're going to formulate this as 2 different functions. We have h of x here, which is the desired mapping of these 2 layers. And then f of x, f of x is just these 2 layers. And then h of x is going to be f of x plus x. So that's going to be this overall here. So h of x is this overall residual function that we're trying to learn here. And so it's going to be residual because h of x is going to be equal to f of x plus x. So f of x, being what the neural network is actually like learning, is going to learn the difference between this optimal desired mapping and just x. So it's just going to be able to say, okay, we're just going to be able to add x now. So at the end of the day, if we have something that's working really well, and then we're stacking these more 2 layers on top, if this just goes to 0, then you can always just be learning x. And then it should never degrade anymore, because if it just goes to 0, then it's going to do just as well as the shallower component right here. So this is just like their mathematical formulation of this here. So in this paper, you can almost get away with not seeing any more math if you just simply understand that. They're just using math to communicate this idea. Now, there is one thing that's probably worth mentioning here, that it mentions of x and f must be equal in equation 1, which is, where's equation 1? No. Does anyone see where equation? Right here, okay. So it's that f where x, where there's a w here, just reflecting that it's being learned here. And then y is just your final output there for the really. So we have the idea it's learning that like residual function. But if you stack these on top of each other, for that, this x is being added to the output here. So this output needs to be the same size as this input. So that's where you might have been thinking that there might be some problem there. So how do they get around that? Well, they would just do some projection into a different dimensional space. And that's why you would have this different w here in those cases. A lot of times they're just able to do it without having to so within here, they don't have to do any update. They can just send it right through because they're designing in such a way that that output is going to be equal to that input in terms of dimensions. So that's like the main idea of this paper right here. We already know at a high level, okay, what they're doing and why they're doing it. they're trying to beat the problem degradation. They get around that by this idea of learning this residual function, so that you could always just have that output of the shallower component if that's the optimal solution. So in every paper, if they're nice, they'll have an implementation section talking about, okay, what hyperparameters did they use so that you could like go and replicate the results. You see that they're using stochastic gradient descent. They're using a mini batch size of 256. They have a learning rate that starts by 0.1 and is divided by 10 when the error plateaus. So they're doing some like learning rate decay here. And then they're saying they're training it for like a ton of iterations. They have some weight decay. They're using momentum 0.9. They don't use dropout. So these are all things just so people could like go back and implement this from the scratch themselves. Then from here, it's mostly just talking about the different experiments they did. They talk about, okay, so you have this new idea, okay, what are we comparing it to? Well, they're going to compare it to plain neural networks, and then they're also going to compare it to VGG, which is this diagram right here. So taking a look at this diagram, this is your normal 34-layer plain. Just if you didn't have the idea of learning this residual, you're just learning a really, really deep neural network now. You're not having these skipped connections here anymore. So you can see VGG19 has all these like different things happening in it. ResNet is just kind of the same idea, just stacked and stacked and stacked and stacked on top of each other. If you go look at the PyTorch code, you literally see how they have like their, actually let's look at the PyTorch code. They literally have this idea of a basic block, and we'll be kind of implementing something very similar to that. And then when they do ResNet 18, they just go and stack all these blocks on top of each other, and that's their declaration for now a model with 18 layers, or 34. So now it's just a very simple like API call change to make. So even like 152, so you don't have to like write out 152 API calls. So that's a paper now, just experiments. They compare different layers, and they show that the deeper it is, the better it's actually doing. Except in this case here. Yeah. This is related to that idea, okay, if that input isn't equal to that output, they talk about different techniques and how you can adjust that. You could like, yeah. If you want to go into that, let me know. But otherwise, just check some code at the end of the day. Now you see they have different blocks here showing, okay, what needs to be different when you have a different input. So if this input equals that output size, then you're totally good to go. If it doesn't, they use a one-dimensional convolution to like just downsample that, take what's necessary. Or actually, upsample that. Yeah, so the end here is just them going over, comparing different things, using different data sets, like all good scientists should do. And then I don't believe this has an explicit conclusion. So never mind on that front. And then some papers will have like an appendix just talking about different things they did that for whatever reason, maybe like there's a conference page limit, so they can only submit so many pages. So they might just add things. You might see other experiments. Some people had experiments that didn't go so well in the appendix, things like that. So just know that if you're really looking at a paper, you should make sure that there's an appendix or so. Any questions on this specific paper? Anything I missed? Anything you want to know on just reading papers?
So are these, so like in the diagram on that page, for example, you have physical basically being between every single two layers.
Mm-hmm.
So are we able to like learn that function? Like, is it a changing quantity of layers? Like, you can learn that function that is zero, or are we specifying this like
Anytime you have that like connection going down here, it's kind of implying that, okay, these two should learn that identity. Yes. So it's like anytime you have that skip connection, it's like imposing this idea on it. So it's like up to the network to decide to learn, okay, when do we need to stop learning something and then just let it flow through.
Gotcha. And each two of those layers and then residual is basically a block.
Yes, exactly. Like you'll have an API where it's like a residual block, like we saw. Yeah. Okay. So in terms of how much time do you want to save for projects? Okay, I'm just going to talk about the code then. So I think, so I just wanted to show, let's talk about the idea of having this like residual block because it will take me more than like 5 minutes. Yes. So you have your standard, like, okay, remember how we did like this PyTorch CNN stuff. You have your standard like imports. We're using Torch. We're using Torch Vision, which allows us to have these different data sets really easily. We just have some hyperparameters. We want to push this on the GPU, so we use this device thing. We need the data to not be in like image format. We want it to be in like a tensor and matrix. So we have this transformation, so it's going to make it we're going to make it a matrix that this network can learn on. We're going to normalize it, which will just help gradient descent like learn faster. We break up our data into train and test sets. We use this idea of a data loader so that we're able to handle things like batch size easily, so we're able to shuffle our data easily. So those are just like very useful Python or PyTorch things to be aware of so that you can handle your data in an easy way, so you don't have to write your own custom like batch size methods. You don't need to like do some NumPy thing to shuffle your data, or if you want to get really fancy and like be able to like load data beforehand in parallel, you don't need to write your own like library doing that. You just set your number of workers to 2. So we're going to have a class called residual block, and we're going to have a class called RedditNet. And so this block is going to be like literally this thing right here, where we have 2 layers and this skip connection right here. And that's going to be that output. So in the residual block, the main thing to look at probably is this forward function here, PyTorch thing. We extend our network.module, so we're able to keep track of these parameters. Just define the layers beforehand, because those are going to be like the same parameters that'll be used and then updated. Then we call these in forward. So what this looks like in code, this whole skip connection idea, this whole residual function idea, is literally just saving that input and then not adding that until the very end here. So we just do the same thing that we did in the past workshops where we have this convolution, apply this regularization thing, which is that normalization technique they were talking about at the beginning that helps extend these deeper and deeper neural networks. So we use a convolution, we have batch norm, and then we apply an activation function, get that wiggle in there. And so this code right here is just my workaround for when this input does not equal that output. So you should be able to try it with like as different channels as you want, and it should still work. It just basically pads zeros in the right places such that they're going to equal the same place. That was one of the options they talk about in the paper. Like they also use certain dimensional convolution so that it gets to that size too. I was just like, let's pad it. It gets rid of those weights too, because if you do another convolution, you're adding in more weights here. So what's happening here? Okay, we've done this before, just convolution, ReLU, and now we're just making sure that it's the right connections, that input is equal to that output, and then we add this residual here, and that's our step connection. Apply our final activation function, and that's our residual block right here. So it's just, we've done all this convolutional stuff before, now you just add that input to that output. And now ResNet would just be, okay, let's take in a hyperparameter, number of layers. And then for range number of layers, let's create this residual block. And so I have this if statement here because the very first input is going to be some RGB image, so you're going to have a channel for red, green, and blue. So that's just going to be 3 channels, but then afterwards we're using 4. Yeah. So we just saved that. We use this thing in PyTorch called the module list, so that it just registers everything nicely with PyTorch. And then at the very end, these are all convolution layers, so the final thing we do is we establish a fully connected layer, and that's just going to be a standard feed for a neural network, which is reflected in this linear neural network class. So now this forward is just going to look like, okay, we're just going to go through all the blocks in our residual blocks that we have. We're going to run it through those, and then we're going to take the output of that. We're going to turn that into a vector now, because remember, you're getting those feature maps. So now we just want a long vector, and then we're going to fold that into our fully connected neural network. And now this output, what we're going to end up with is 10, because we're using the Cypher 10 data set, which, just so there's some images in your head. Let's check it out. So there are 10 classes in Cypher 10, hence the 10. So they have pictures of airplanes, they have pictures of automobiles, birds, cats, etc. 50,000 training images and 10,000 test images. And these are 32 by 32, 10 classes. So when we initialize this model, we're going to have 10 classes here, so then we're going to get 10 values as our output. And then this softmax here is basically going to really emphasize that max value that's coming out there. So that's what's happening there. So now we initialize it. We say 10 classes, 3 layers deep, push it onto the GPU. The loss function we're using is cross entropy loss, and that's just really useful when you have like classification problem instead of like a regression problem, like you need to distinguish between different discrete values. And then optimizer, we're using Atom, which is a variant on top of gradient descent. It just lets us not have to worry too much about our learning rate. We passed out our parameters because that optimizer is going to be updating the parameters in our model, and then we start training. So for training, we're going to go through a certain number of epochs iterations over this data set. We're going to keep track of our loss, and then we're going to iterate each batch in this train loader that we have here. And then we're going to pass that data onto the GPU as well, so it meets the model, which is also on the GPU. Then we have this PyTorch specific idea that we zero out the gradients that are accumulated, and then that way we make our prediction and get a prediction from that, and then we get our loss, which is going to be kind of the difference between the predictions and the labels. And then from that loss, we're going to take that loss and use that to do our backpropagation, which is just a back.backward call. And then we calculate those gradients. And then based on those gradients, we're going to take the optimizer and we're going to update the weights in our model. And then we're just going to keep track of this running loss. And then we're going to learn. And then we're going to get an accuracy metric. And after a little 10 epochs, we get a 43.5% accuracy. Random would be like 10%. So it is doing better. And we are employing this idea of a skip connection. So from math to code, from paper to code, we basically have this idea of saving this input and then just adding that to the end. This is a very simple example. I wouldn't recommend using that in practice. Use all this nice PyTorch thing that has all this nice API built out for you. But if you look at here, we're doing pretty much the same thing. We have our 2 convolutions. We're using some normalization. We're using ReLU. Then they save the residual here in the beginning, and they're not going to add that until the end. They have a different way to handle when the input doesn't equal the same size as the output, which is what this downsample method here is. They also have a different idea here called the bottleneck, which I believe is a different, I believe it has to do with these in-planes and planes here, how they do that differently. Don't take my word for that, though. Then in ResNet here, you see it's taken in layers as a hyperparameter, number of classes as well. Then it's going to go through each of those layers, which is multiple of these blocks. See layers that append this block type thing. So you can see we're doing the same idea here, just broke it down a little simpler. But yeah, that's from code to paper in a sense. Any questions before we go into like just talking about projects? No. Alright, projects. So I have a document in Piazza with just project ideas. So there are a couple different kind of sections. So I added these sections, kind of like Julius is working on like interpretable methods, maybe just build an API from some already known interpretable methods in PyTorch. TensorFlow already has like some good cool stuff, so if you want to like port something like that over from TensorFlow to PyTorch, that'd be a perfectly valuable project. There's this really cool paper that came out talking about all these different problems that machine learning could help with climate change. So it just basically lays out all these different problems, what problems are like most important. So if you want to try to solve climate change with machine learning, you can do that here. Then there's a section like, okay, if you just want to pick a paper and then implement it, like do what we did today, but much more in depth. Like just take a paper, read through it, kind of spend some time, understand what's happening, break down any equations that are in it, and then just convert that into like PyTorch code. That is a very reasonable and nice project to do. You can email the author of that afterwards and be like, hey, look what I did. And they'd be very happy to see that. There's like one paper here, which is neat. It's like an evolutionary method of making neural networks. ResNet, if you want to build like ResNet out fully from scratch, if like today captivated your imagination, then feel free to go and like build this out in depth, kind of matching what like PyTorch has done. Like just have a nice API where you can create like ResNet 34 and stuff. Play around with hyperparameters. Sorry, what? Neat. Yes. Feel free to put your name on one of these projects. Like comment and be like, oh, I want to do this. Here's the comment there. Like, oh, I'm going to do this one. And then like if you want to do that, people could like contact each other for teams if you want to do that. Otherwise, just keep quiet. Have no one contact you. Do a transfer learning project. Take like some model that's already out there, apply it to some new data set, like we did on ResNet. Apply that onto some new problem that hasn't been applied to before, or maybe if it has been applied to before. There's no expectation of doing something like super original or creative here. If you literally just want to like get your hands dirty, like just go for it. Do some little projects. Have something to show for it. Just have a nice little project to put on your GitHub. Julius added some helpful links here with a bunch of different data sets. So if you want to do a Kaggle competition, that's a totally valid project as well. So if you literally just want to like go into some competition and be like, oh, let's do LIFT's 3D object detection for autonomous vehicles, then you can go through, learn what 3D object detection is, take a look at the data they provide, and see if you can build some model here and submit yourself for some competition. That'd be cool. You could win $25,000. So, just saying. But yeah, like feel free, like anything you can think of. You want to do hot dog, not hot dog from Silicon Valley, go for it. Or any other respective meats. Go for it. Yeah. Anyone having a project idea they want to like bring up, see if you want to find a team member, have any ideas? Or just if they have a general idea and they don't know specific, looking for guidance on that. Anything. Yeah. Mm. Yeah, that could, like, if you had GPT-2, like, you can, like, download some version of it, like, already pre-chained, and then convert your data set to, like, yeah. Yeah, that you could totally do that. Yeah. Put it down on the sheet, see if you want any teammates. Like, feel free to add your ideas to this document. Like, that's what this is here for. So, yeah. Anyone looking for teammates, if they just want to, like, make a team right now and then come up with an idea, feel free. Yeah, start brainstorming. Does anyone just have, like, a general idea of what they want to do? Like, okay, I want to, like, do natural language processing, or I want to do, like, some image thing.
Yeah, so it's kind of like similar to Saturday, but with this idea of like music generation, except I want to use like GANs to generate electronic music.
Okay.
Because kind of with, I guess like for example, like music generation with like a piano,
Yeah.
like music, when you can like use, I guess notes and representations like a string and have like a language model like kind of recognize the patterns to generate something new. With like electronic music, there's like filters, there's like cuts, there's like a drop.
Yeah.
It's, I don't know, it's just different.
Yeah.
So
Yeah.
I'm not sure how to approach it, but I found the papers
Yeah.
on like how they do it for just music in general.
Yeah.
I know TensorFlow has Magenta,
Okay.
which is like used for music and audio in general. So
TensorFlow, Magenta. So essentially using a GAN to generate music.
Yeah.
I would say GANs have not been very good at doing that.
okay.
What's it called? What's it called? So it's going to apply our techniques learning papers that we just learned. Or not that one.
A cramp is no small danger on a swim.
So you can make anyone say anything if you have enough data.
2 plus 7 is less than 10. Clothes and lodging are free to new men.
We'll be doing GANs next week, so I'm sure that's going to inspire a lot of ideas. But yeah, like if you want to get started on that, I would probably say recommend like implementing a paper that's already out there, and then seeing if you can build on that. And just that implementation would be like your project, and then you can push it as far past there if you want.
Yeah.
Yeah. Anyone else have just general ideas from brainstorm? Yes.
You have to follow the kind of using machine learning to reduce in-house emissions or like
You could tackle a problem. Like as long as there's machine learning, you're good. Ideally, you apply like some stuff we talked about in here, but if you want to just like dig into something on your own and it still makes sense for this class, then go for it. At one point, we will be doing like, okay, like write a little paragraph of what you want your product to be, and then that's what we'll be like looking at throughout the semester. That can still change a bit, but just so we know what everyone's like working on. So expect that in the next like week or so. Yeah. Yeah. Have a nice night.